Merci pour cette présentation. Je vais remercier le Comité français de mécanique des roches pour l'invitation de prononcer cette conférence. C'est un honneur que j'apprécie vraiment. Et maintenant, comme elle a dit, je dois m'excuser parce que je vais continuer en anglais. C'est plus facile pour moi, mais surtout c'est beaucoup mieux pour vous. This lecture is in honor of Jean Mandel, who was the first president of the Comité Français de Mécanique des Roches. I really appreciate this invitation, especially because we know that France has always been very much at the forefront of the advances in developments in rock mechanics, with a number of very illustrious names that I don't need to recall. I learned this morning that this committee was actually founded in 1967, but I'm also aware that in the early days when there was this Salzburg geomechanics meetings, there was always a very strong French presence there, and that was actually the forerunner of the International Society of Rock Mechanics. Anyway, going to business, we are going to talk about argillaceous materials, which means that fine particles predominate. They are apparently very widespread. It's reckoned that they constitute more than 50% of the global sedimentary mass. They outcrop about a third of the emerged Earth surface. There is a big variety of names in which they are used. We are not going to get into nomenclature, but certainly we are going to span the full range from something which is usually described as stiff overconcentric clays, like here on the right-hand side, or rather hard argillites, like the picture on the left-hand side. And that means that we are occupying an intermediate position between hard rocks and soils. I understand that in the organization of this meeting there is also a role of the Comité Français de Mécanique des Sols, the Comité Français de Géologie de l'Ingénieur. So I thought it was an appropriate subject to be in that transition zone between soils and rocks. Of course, the argillaceous materials, argillaceous rocks made of plastic clays or indurated mud rocks, have been intensely studied in recent decades, mainly because of the interest as a possible host medium for the deep disposal of radioactive, high-level radioactive waste, because they have low permeability, significant retardation properties, not much economic value except in special cases, and some sealing capacity. Of course, they are quick rocks, so they require support in excavations. They are more sensitive to chemical changes, and if there is an increase of temperature, there are overpressures that are generated, as we'll see in the later part of this lecture. And because of this interest, there's been a number of underground labs where excellent research has been done, 4 of them in Europe, the Opalinus clay in Monterrey, in Switzerland, the Boom clay in Mol in Belgium, of course the Bure underground lab in Cox Claystone, also the Tournemire lab, and so on. And actually I've collected, reading for these lectures and reading on this subject, there is quite a number of clays that have been intensely studied. I put them in a geological column. They actually span the full geological column, and I actually stop at the beginning of the Mesozoic. And I also highlighted in blue some of the materials that we are going to give some prominence in this lecture. Just to give some background of properties, here we have some typical values. Actually, there are many instances outside the range, but just to give some idea of the numbers we are talking about. On the left-hand side, the two left columns are indurated mud rocks or stiff clay stones with a low porosity and higher strength and Young's modulus. On the right-hand side, the other two columns, they are more plastic clays, sometimes even describe it as soils, like the London clay or the Boom clay, with a higher porosity, lower strength, lower Young's modulus, but in all cases, obviously, the permeability is very low. Okay, so this is, after this introduction, we can look at the outline of the lecture. I'm going to talk about mechanical behavior, focusing only on strength, on phenomena like brittleness and anisotropy. A brief mention of hydraulic and coupled hydromechanical behavior, and some field cases regarding either slopes or underground excavations. And then we'll introduce, towards the end of the lecture, briefly temperature, focusing only one aspect, the overpressures that are generated by thermal effects in these materials. So let's start with strength. These materials, they tend to fail in a brittle manner. I simply define brittleness, but when we go to the peak, after the peak there is a significant loss of strength. These are a test, and ring shear test, on a Spanish clay that we studied some time ago, and we can see that as we continue shearing or we continue displacing one piece of the clay over the other, we reach a final minimal and stable strength, which we call it residual strength, and that strength can actually be quite low. When this residual strength is achieved after significant movement, usually 200, 300, 400 millimeters, and in the field it usually manifests itself in these striated surfaces, or silicon-sided. But the interesting point is that when we look at the clay in those shear zones, in these on these localized zones, we find that the clay particles have actually oriented themselves in the direction of the shear on the displacement. And that explains these very low values of strength, because what we are measuring are frictions between clay minerals. And this is a typical result. Here we have clay fraction, we have here friction coefficient. We see that the clay fraction is small, the actual peak and residual is actually very similar. They are ductile, because the coarse particles which are in there actually disturb the clay fabric, and they don't allow the clay to align itself and to form these very oriented sliding surfaces. But as the clay fraction increases, we can see here, obviously the peak strength reduces, but the residual reduces even more, the distance increases, brittleness increases, because here there is enough clay that this oriented fabric can form and provide this low residual strength. And we obtain that all the time. These were artificial materials. This is a classical paper back in 1998, but more recently, for instance, in Opalinus clay, the material in the Monterrey lab, there are faces which are more clayey, others which are more sandy, so you end up with samples with different amounts of clay. And we obtain the same picture of results. This is the peak coming from triaxial test. This is the residual coming from ring shear. This comes from some results from Alessio Ferrari and co-workers, and we can see that we get the same pattern, the large difference, large brittleness as the clay fraction increases. To illustrate the really deleterious effects of residual strength, we can just show an example which is the Panama Canal, which actually goes mainly north-south. South is Pacific, north is the Atlantic. In fact, it was initially a French initiative, which was defeated mainly by yellow fever and health problems. Then at the beginning of the 20th century, US took over. They managed to control the yellow fever. Medicine had advanced. They also abandoned the idea of the sea level canal to make things easier. And in spite of all that, there were major landslides that we are going to have a look now. It was opened in 1914, but even so, the major landslides have continued. The last big one was in 1986, and which has led to the canal being shut down on at least 26 occasions totally, and other times partially. The problem, this is the geological profile of the Panama Canal, this is the Pacific end, this is the Atlantic end, and the problem is here. This is the continental divide, and here where the excavations reach maximum depth, and unfortunately they coincide with the presence of the very infamous Cucaracha Shale. You can see here a rare photograph from the Lesseps initiative. This is in the continental divide, it's rather stiff slopes. This is the continuation by the US, still rather steep slopes. Things were going well, but at the end of 1910, and especially from 1911 on, the major landslides started. This is the Cucaracha slide of early 1911, another one in September. There were many. Another one in the West Culebra location in 1912, so much so that they ended up flooding the canal and actually removing the material by dredging because it was more efficient than by terrestrial mills and so on. There were three main areas of all under very similar circumstances. Is Culebra, West Culebra, Cucaracha. These are two hills which remain more or less intact. It was opened, as I said, in 1914, just in time for the First World War, but the slides continued. This is one in 1915. This thing here is the toe of the slide that has appeared in the middle of the canal, so it was coming up here. And that was the last one, big one, 1986. The canal partially open, but quite a lot of dredging going on. There is still dredging going on at present. And to show, and the reason, obviously, the culprit was the Cucaracha Shale, which has the classical brittle behavior. This is the peak strength, quite a range because it's natural material. This is the residual. Now here, in fact, there is also a range of residual, but the average, which I think is a bit low, but it's certainly 7.5 degrees. Perhaps in reality it's a bit larger, but certainly not much larger. So that's the reason. And just to show the effects of residual strength, this is in red, the design excavation as it was and how it was progressing. But from 1911 on, we had landslides, and in 1969, the surface, which was original there, it's come down to this. It's adapting to the residual strength. If you do a cruise in the Panama Canal, which is possible, and when people go by, they look at this. This is the Gold Hill, this is Contractors Hill. But for us geotechnical engineers, the interesting part is here and here. These are the East Culebra, West Culebra slides. You can see that the bank has practically disappeared, and it has finished more or less sliding because it has adopted a friction angle which is very close to the residual. Okay, that's not the only feature of the brittleness and strength of these materials. There's another one that's been frequently observed, that after reaching peak, sometimes you get quite often, a very strong loss of strength with very little displacement, then something which looks stable. This is not, these are triaxial tests, this is not the residual, you don't get to residual in the triaxial, but it's an interesting point, and it was baptized as post-rupture strength, I think was by Berland in his ranking lecture, and that name has actually stuck, so we talk about post-rupture strength. And this is usually attributed to the loss of bonding, which doesn't require much displacement, especially if the bondings are not very strong. And the result is that you lose most of the cohesion, if not all, and you lose very little friction. Another observation is that we don't know very well how to interpret it, that this post-rupture strength and intrinsic strength would be the strength of a reconstituted material. They're usually quite close, which is perhaps not surprising because there is not much bonding present in a reconstituted soil. And again, this behavior is confirmed many times. I just got a paper from my friend Michael Vardanis, who's been doing drain direxia tests recently on a number of Greek mals. For instance, on the left, we have Attica mal, on the right-hand side, the Verni mal, and you can see very clearly this sudden drop of strength down to the post-rupture strength. And if we put together the failure envelopes, we can see what we were just mentioning here. This is the peak, the post-rupture. It has actually lost most of the cohesion, but the strength, the friction angle is nearly the same. The same for the Bernoulli-Mal. This is Corinth Mal, which actually was involved in the excavation of the Corinth Canal about the same times of the Lesseps expedition. Here he also tested reconstituted material. We can see that they reached this post-rupture strength. So this is the peak. This is the post-rupture reconstituted material, very close. Friction has not disappeared, but cohesion has nearly gone. And this is the residual. Here they were lucky because the clay fraction and the plasticity index of this mal is very, very small, so the residual angle is quite large, as you can see, about 30 degrees, so you could actually get away with rather large, rather steep slopes, as you can see in the pictures. So we can bring all this together in a kind of a conceptual framework which goes back quite a long time, and the first time I saw it explicitly stated was by Simpson in 1979, is that we have two stages in this reduction of strength down to the residual. The first one due to the loss of bonding, in which we lose most of the cohesion but very little friction. And then the second stage is due to particle reorientation, which accounts for this very low friction angle. Cohesion is not lost, so the little that is remaining gets lost also at this stage. And this also provides a kind of framework to discuss the strength of discontinuities. This is London clay. It will appear a few times because it's a very well-studied clay. We can see that there are joints in London clay, like any rock, with making families oriented in the same way. But they also have fissures, which are more random oriented. They are shorter. But if we actually look at the strength of both joints and fissures, we ended up with something very close to the post-rupture strength and therefore also the intrinsic strength. Another example, that's Santa Barbara clay, tested by Calabrese. This is the resistance along a joint. This is the peak one. But interestingly, if you recover the material from the faults by definition have large displacements, then what we get is the residual. So even the strength of discontinuities actually fit quite well in that framework. And finally, a couple of words about anisotropy, which we'll see later on that is actually significant. This is Opalinus clay from Monterrey. You can see when tested parallel to bedding, we have a stronger material and a stiffer material than when we actually load it parallel to bedding. This is similar results. This is on London clay tested in the hollow cylinder apparatus, and the variation of strength with the orientation of the loading. You can see this is the perpendicular to bedding. There is a minimum around 45 degrees, but when parallel to bedding, like Opalinus clay, has a higher strength. And because you can measure quite a few things in here, you can actually identify two different sources of this anisotropy. One is the variation of the friction angle with orientation, but the other is also the change in direction of the Andrean stress path. So it's the combination of these two that actually end up with this anisotropy of the Andrean shear strength. Okay, so if I can summarize the lecture so far, let's say that these materials tend to fail in a brittle manner, that often this reduction of strength comes in two stages, one associated with the loss of bonding, in which we lose most of the cohesion, if not all, and the second associated with the reorientation of clay particles, in which the friction can actually achieve very low values. The strength of discontinuities seem to fit also this idea. And finally, well, I just mentioned anisotropy, that you are going to see that in some cases is a key feature to explain behavior. Just a few words about hydraulic and coupled hydromechanical behavior. This is a collection of this guy, Dechos and Neusin, actually collected permeability determinations in these argillaceous materials, but only the ones that they thought they were reliable, because it's sometimes not easy to measure. They ended up with this relationship. I have added some of which that we have working on. They fit well here. Obviously the permeability is always low. It reduces with porosity, but perhaps the most significant feature to highlight here is that for a constant porosity, there may be 3 orders of magnitude difference in the permeability, which reminds ourselves that porosity is not the important factor in this case. It's the fabric, it's the size of the pores, and so you can have quite a spread. I mean, for instance, this is again London clay. There is taken from 2 different layers with different amount of clay for different fabric, and you can see there is a couple, for the same porosity again, there is a couple of orders of magnitude of difference in the permeability, which are always quite low. The coupling, hydromechanical coupling in soils is very easy. It comes defined by Terzaghi's principle of effective stress, but things are not so easy when the materials become stiff, like in these stiff clay stones that we have already mentioned and we'll see later on. If we stick to poroelasticity, this coupling can be defined by the Biot coefficient, which may be isotropic or anisotropic, and obviously, since it controls effective stresses, is an important parameter, and there has been plenty of measurements trying to identify this parameter with a very big scatter, some values which are not really credible. There's been quite a bit of clarification on this here by the work has been done at Sermes, in the group Pierre Telage and Jean Solem, in which they actually try to measure for the Cox clay stone very carefully the Biot coefficient. They did that in the traditional way, in which you apply a cycle of mean stress, you apply a cycle of pore water stress, and if Terzaghi holds, they should give the same result, but it doesn't, and so they found in this particular case values around 0.86. But you can do it independently, and they did, using unjacketed tests that allows you to compute the stiffness, the volumetric stiffness of the solid phase, and they obtain a very similar result, which actually gives confidence on that this is probably quite right. They did more tests and they ended up in this range between 0.85, 0.91. Also, more or less at the same time, Opalinos clays were being tested in a similar way, and they end up with values around 0.9. So it seems that, for these stiff clay stones, this coupling Biot coefficient is not 1, but it's not very far from 1, and it's likely that when we reach failure, it's gone up to a value of 1. I'm not going to say any more here, and we are going to look at 2 cases, quite different. The first one is slopes in London clay. I'm bringing this here, although it's rather a mature subject, because it has been extremely influential to develop the present ideas about progressive failure, brittleness, and so on. One thing that was puzzling the geotechnical community for some time is that the cuts in London clay failed. Many studies failed, but interestingly they were failing many years after they had been excavated. For instance, these are 2 examples actually coming from Skempton's ranking lecture, in which this one on the left, which is the North Hall one, failed after nearly 20 years, and this one in Sudbury Hills actually failed after nearly 50 years. And so that created a puzzle. A puzzle also was compounded by the fact that when you back calculated the strength explaining the failure in a number of places, you could get a failure envelope, which turned out to be very close to the intrinsic or the strength of the reconstituted material, which we know now is similar to that of the post-rupture. Very different from the peak, very different from the residuals, somewhere in the middle. Also, interestingly, when the back analysis was performed on reactivated landslides, they found that the residual strength was operational there, around 12 degrees in the case of London clay, which means that once you got to residual, there is no way that the former strength can be recovered. That's not strange, because it's difficult to envisage how this oriented fabric could actually be rearranged into a different pattern. So that was quite clear, but the first time slides was creating a puzzle. Well, if we go briefly back to the Panama Canal, the same picture actually arises. These are the values of first slides in the Culebra site, very close to the reconstituted material. When they were reactivated in the 1990, 2001, what they were showing obviously was residual strength. So, and initially that gave rise to some theories which later on they were proved wrong. The initial theory, actually supported by very illustrious people, was that there was a progressive loss of strength which was affecting mainly the cohesion due to water infiltration, softening of the material. That's how the term fully softened appeared. No? They reached something called a fully softened strength, and then it fell. Obviously, after failure, went to residual, and during this thing was actually the friction angle reduced. But doubts on these mechanisms were first cast out by the observations of Peter Bohn, Jem Balvanke, which they measured pore pressures in cuts in London clay, the ones that had not failed, and they found that the pore pressures they were measuring, they were actually quite far from equilibrium. And in fact, the times required to reach equilibrium were not that on the same order of magnitude of the times that were being recorded of times of failure after the excavation. So they say that the observation suggests that the equilibration of pore pressures in London clay may be slow and occurring over a time comparable to the delays of failure commonly observed. In fact, when you put together those back analyses together with, those observations together with the back analyzed pore pressures from the failures, they came out on a very nice single curve. So that's taken from the paper. These preliminary observations, they are not preliminary anymore because they've been confirmed, suggest that failure of cuts in London clay may be delayed primarily by the rate of pore pressure equilibration. If this is so, and that's the important statement, it's unnecessary to presume a significant drop in drain strength with time. So you didn't have to postulate an additional mechanism a bit out of nowhere. Of course, why the reason why the back analyzed strength was somewhere between peak and residual comes from the realization that brittle behavior leads to progressive failure. And in a progressive failure, along a landslide, there will be some parts which are residual, some parts which are at peak, sometimes somewhere in the middle. So what you calculate is not the strength of the material, it's an average over an average strength. It's wrong to think of a single strength. And all this could be actually demonstrated and using simple finite element analysis without any assumption, just putting the brittle behavior of the material and just allowing the pore pressures to recuperate according to the permeability of the material. Nothing else. And that was done by Post. We did that in a two-stage, going from peak strength to pore rupture to residual strength. The results were similar, and we can see that certainly you get failure decades or many years after the excavation. It's a progressive failure. Here it has failed along this this area here, and then it will continue until a full sliding surface and a full loss of equilibrium occurs. And this is the evolution of the peak, post-peak residual strength compared to the stresses which are applied, and you can see that there is a variety of strength operating at any time. So that creates the question, not easy to answer, say what is the operational strength? In a sense, what strength I should use for design? I don't think we can give a single criterion for the reason that this average must depend on the geometry of the problem, on the scale, on the brittleness, on the rate of degradation of the brittleness. All these factors must play a role. So it's unlikely that a single size fits all. Anyway, if we take this residual factor, which was defined by Skelton, which is in terms of averages, where are we in this back calculated strength between peak and residual? On average, obviously, that's the only thing you can do. We find that in the slopes between 0.4 and 0.6. In Carsington Dam, that was a very important case history because it cleared up a lot of misunderstandings about progressive failure. It's between 0.4 and 0.5. The Admiral Queller Dam, a tailings dam that fell through a foundation failure, we found around 0.4. But so it seems to be clustered between 0.4 and 0.5. But for the reason I was saying before, I think it would be wrong to actually use that as a general rule. In fact, that was already said by Bishop, even before anything of this. He said in 71, it's unwise to generalize on the basis of slopes where the geometry, scales, and soil properties vary only a limited range, until the relative importance of these variables has been established. And actually he was saying, until we have an efficient analytical method to clear this up, it will be difficult to make any statement. Well, now we have this analytical method, we can do finite elements or other numerical methods, but I think the conclusion up to now is that it would be wrong to take those cases as a guide for other very different situations. So if I summarize this part, it has been demonstrated that poor pressure equilibration controls the time of failure in this type of problems. And if we have brittle behavior, progressive failure will occur because we are always in situations of non-uniform stresses and strains in the field. So because the operational strength, the back calculation strength, the design strength, if you like, depends on so many factors, it's unlikely that a general criterion to select the value for this design will be actually found. What has been really abandoned is the concept of fully softened. There is no such a thing. The fact that the pore rupture strength seems to explain many of these failures, I think, may be a bit fortuitous. Of course, numerical analysis provides an attractive way to tackle this problem, but they are complex, they are not as straightforward, so I think we are still a long way away to that this is going to be a routine design tool. Let me go to underground excavations. Here we are not going to residual because the excavations are usually supported, so they don't go very far. I'm going to talk about excavations in the Bure underground lab, and here I take this opportunity really to thank Andrea because for the support, not only for the work I'm going to present, but in many other projects. I'm sure that all of you are quite aware of this laboratory excavated in Cox, about 500 meters below the surface. So I'm going to spare myself to talk about the properties of this material, but obviously strength, the material is brittle, and strength and stiffness are anisotropic, like in most materials anyway. This is the layout of the lab. What is important here is the in situ stresses which occur in the lab. The major Well, first of all, there is a vertical stress which is more or less equivalent to overburden. And the horizontal stresses are not isotropic. There is a major one, which is about 1.3, the vertical stress, and a minor one, oriented at 90 degrees, obviously, which is quite similar value to the vertical one. So, and very nicely, Andre excavates the tunnels, the galleries, in the direction of the major minor principal stresses horizontally, which actually helps with interpretation. Obviously, if you are interested in radioactive waste, you are interested in the EDZ, and there has been some excellent comprehensive work in characterizing that EDZ, which is not the place to describe here. But the summary of it is that if you excavate parallel to the minor principal stress, in which now we have an horizontal stress which is larger than the vertical, the EDZ develops mainly on the vertical direction, very little horizontal. Also, the convergence in the vertical direction is much larger than horizontal. If we now take excavation in the perpendicular direction, this is now parallel to the major principal stress. So now in a cross section we have something which is more or less isotropic in terms of in situ stresses. But as you can see, the development of the EDZ, the excavation damage zone, is certainly not isotropic. It develops a lot horizontally, only a little vertically. And again, now we have horizontal convergence larger than vertical. Okay, so we are going to try to model the development of this EDZ. This is a work that was done especially by Manica. This is the rather simplistic constitutive model, but with a number of added features which make it quite useful. So we have this hyperbolic Mohr-Coulomb surface as the main yield surface, but hardening and softening is actually established by the variation of the friction angle, cohesion, asymptotic cohesion, and tensile strength. Obviously, the degradation of cohesion is much faster than the friction angle to keep into this two-stage brittleness model that we were seeing before. Also, the strength is anisotropic, and this is the one we are going to use in the lecture I'm going to show. There is a minimum around 45 degrees, a maximum when loaded parallel to the bedding. There is a variation of permeability with damage, well, to be precise, with plastic strains, and we take this cubic form that was introduced by the people at Liège, some time dependence, which is not going to figure today, and because we are into softening, we need some regularization technique, and what we use is a non-local formulation in which what happens in a Gauss point depends on what's happening in the Gauss points in the neighborhood, and this is the weighing function that we use, this red one, which is due to Galabi and Schweiger. So putting all this together, we try to analyze in two dimensions, in which excavation is actually approximated by this deconfinement curve. The details are in a couple of Jettenique papers by Manica et al. We can see that it's a very fine mesh. You need to find meshes in non-local formulations because you need a number of Gauss points around the Gauss point you are considering, so you need a fine mesh for that. And now we can see the results in terms of EDZ development. Here on the left is the excavation parallel to the major principal stress, so the cross-section in situ stresses are actually isotropic, and we can see how the EDZ develop with these localized zones, ending up with a configuration which is actually quite similar to the one I was showing before, the one that have been observed. If we move now to the right, excavating in the perpendicular direction, now we have a horizontal stress higher than the vertical, and we do the calculations, you can see that now it develops mainly in the vertical direction, again quite similar to the observations. It's also, there is more benefits from this analysis. For instance, looking at the flow of water. The flow of water gets concentrated in the localized zone just because we have this increase of permeability with plastic strains. These localized zones actually concentrate the plastic strains, and that's where the flow occurs, which means that the region around, at least the horizontal one around the opening, is relatively well drained, or better drained due to these localized zones. And that explains some observations. For instance, here in dashed lines are observations of pore pressure in a horizontal profile at increasing distances from the opening. And contrary to what if you do an elastic analysis, you'll get a maximum pore pressure generated close to the opening. Here the maximum one is towards the edge of the EDZ, because this part, as we have seen, is relatively well drained. And we can see that the calculations also show the peak a bit lower than observed, and also a reduction with time, which actually seems to fit reasonably well observations. In fact, pore pressures were measured at 6 months, 1 year, 2 years, 3 years. These are the results at different times, and actually, again, the model seems to be able to capture this variation of the pore pressure with time. If we believe that that numerical model has some correspondence to reality, one can actually explore the effect of different parameters. For instance, if we take excavation parallel to the major principal stress, so we have this isotropic stress state. Obviously, if you use an isotropic model, we'll not get this anisotropic EDZ. If you only introduce the stiffness anisotropy, you don't get the right result either. You only get the right result when the strength anisotropy, which is the key factor here, is introduced. In the perpendicular direction, you can see in the three hypotheses, the configuration of the EDZ is not that different. It seems that in this particular case, the initial stress state is the dominant factor rather than the stiffness, the anisotropy of the material. We can also check how is the different distributions of strength, different types of anisotropy, what results do you have? Again, when I'm parallel to the major principal stresses, if I use number 1, which is similar to the one I was showing before, you get the right result, but not so much when you use other distributions, which seems to, it's a kind of evidence pointing towards a certain type of distribution of strength. Again, when we go to the non-isotropic stress state, this stress state dominates, so for the three ones you still get quite a large vertical development of the EDZ, similar to observations. So I can now summarize this bit. Brittle behavior leads to localized fractures in the rock adjacent to excavation, which they constitute, they are a component of the EDZ, and that configuration is controlled by brittleness, strength anisotropy, and in situ stresses. In different, the importance of each one is different depending on the orientation. The water flow and pore pressure evolution are strongly affected, as we have seen, by the presence of these localized zones, and it seems that with the formulation used, we get a reasonable representation using this numerical model. Let me finish quickly just saying a few things when we introduce temperature. I'm just going to, of course, there are many aspects. The behavior actually depends on temperature, and we have modified the models to take that into account. But here I'm going to refer only to the overpressures that appear in this type of rocks when we increase the temperature, because it's a very interesting and very showy sort of phenomenon. Obviously, there are consequences in the sense that thermal effects may enlarge the EDZ, may affect the EDZ, and also if you add all these thermal effects of a whole repository, if you put them very, very close, they could lead to some kind of tensile failure. The only way to approach this problem is obviously through a couple formulation, which involves solving the mass balance of solid, water, energy, and momentum or equilibrium, introducing the Fourier's law for heat conduction, which is the only relevant heat transport phenomenon, and so on. If we take the mass balance of water and we introduce there the various dependencies, you end up with something like that, which allows us to see what are the various phenomena which actually result in this overpressure. The first one is the main culprit, the main driving force, which is the differential thermal expansion of the liquid and solid phases. The next two are the variation of the volume of these phases, not due to temperature, but the other things like solid pressure and pore pressure. The fourth is the deformation of the whole skeleton, which also plays an important role. And finally, the fifth is the water coming in or out of this representative elementary volume, because the permeability is low, but it's not zero. And all this, the interplay of all these phenomena is what gives you the pore pressure. If you simplify the problem and assume undrained conditions, so there is no water going in and out, actually, Bou, Arman, and Plua have very nicely derived the equation for the coefficient that relates the increase of temperature to the increase of pore water pressure, and we can see here that the usual culprits appear. This is the differential thermal expansion of the phases, the stiffness of the material, the compressibility, the volumetric stiffness of the solid phase and the water phase. And we obviously you have to check that your code, because sometimes there are subtle things in the codes that don't consider all these things, that your code actually are giving you the right result. What is important is, because the thermal expansion of the water is the driving force in all this, is to use the real one, which is actually variable with temperature. It's 0 at 4 degrees C, when there is a maximum of density, and you can see that from this 0 value it increases significantly as you move up with the temperature. Okay, so we are going to see how all this plays together in a not experiment. This one back in Monterrey. Oops, that's moved, sorry. It should be here. It was performed in this niche. This niche was excavated. 150 millimeter borehole was drilled, and 2 heaters were installed. You can see here. Heaters that were actually expanded against the rock, so there is no backfill. This is a direct experiment on the rock, and the rest are boreholes for instrumentation. This work was done very much with, together with Benoit Garit. This is the excavation of the niche. You can see the Opalinus clay. This is the drilling of the borehole. This is the installation of the heater. And what we are going to show some results of a 3D analysis. Why 3D? Because here the bedding planes are at more or less 45 degrees. And we want to introduce the anisotropy of stiffness, thermal conductivity, in situ stresses, and so on. So you need the 3D. Let's look at some observations first to give an idea of what's happening. This is the central borehole, the heating borehole. This is, we are measuring 1 meter distance in the direction of the bedding plane. You can see the temperature increases, then the heater power is increased, and it increases more, and so on. And this is the reaction of the pore pressure, which you can see is strong. It reaches here 4 megapascals, so it's not trivial. 4 megapascals is approximately what is reckoned, it's difficult to measure, but it's reckoned to be the minimum principal stress in Monterrey. But it's also interesting that the temperature keeps rising, but the pore pressure reaches a maximum and then actually drops because of dissipation. The permeability is low, but it's not zero. These are some results. This is the pore pressure contours. I'm not showing temperature, which are not very interesting. The contours of pore pressures around the borehole, but as time goes on, you can see this maximum pore pressure actually, because of this dissipation, moves away from the borehole. And these are the comparison with experiments. In this same point that I was showing before, we can see here that we predict a faster increase of pore pressure than was measured. We feel that perhaps there was some error in the pore pressure sensors, because in the second round, actually, the rate of increase measured and observed is quite the same. Also the degradation, and also the drop that you get once you switch off the heater. We can look at deformations. There were two boreholes with the sliding micrometers, and just going to look at this one, which was going through the central part of the heater, below, as you can see here. This is the heater, below. These are observations at different times, and we can see that here we have extension close to the heater, partially compensated by compression away from the heater, and we can see that the comparison with the experimental observations, which are these orange quadrangles, is actually again picked up throughout by the analysis throughout it all. The values are very small. The deformation is not large, so it's probably in practice not very important, but it's nice to find that you get that both close to the heater and away to the heater, when there is some compression followed by extension. Excuse me. We also, well, I didn't have time to talk about the constitutive model, but there was a damage component, so we could get contours of damage. And we tried to see whether that was realistic. And here we have the distribution of damage at different times. What we did was to get samples at different distances from the heating borehole, and these are the unloading modulus measured in the lab from those samples. These are the predictions. We can see that there seems to be some damage close to the heater, but if anything, we are underestimating that damage. There are many other heating tests, which obviously we will need more time, but I just wanted to bring this one as a recent one performed by Andra at Bure, in which there is not only one borehole, heating borehole, but 10, and they have actually provided quite convincing evidence that they managed to crack the cocks just using thermal effects. But that would be the subject of another presentation. So, if we look, one of the advantages of using numerical analysis is that you can look in detail at the results. So you can, for instance, look at the couplings and see whether they are strong, moderate, negligible. So if we go from thermal to hydraulic, due to this pore pressure generation, there is this strong coupling. Also some more moderate coupling due to the changes in fluid viscosity. From hydraulic to mechanics, obviously there is changes in effective stress, so there is a mechanical effect. But it's moderate because these materials are stiff and they don't deform very much. And then, because they don't deform, the thermal conductivity is more or less constant, and therefore the coupling from mechanical to thermal is actually negligible. If we do this same road in the opposite direction, obviously there are a strong coupling from the temperature to the thermal expansion of the material, more moderate from mechanical to hydraulic through the variation of permeability with plastic strains or with damage in this case, and again from the hydraulic to thermal, the effect, because heat convection is negligible, there is no change in thermal conductivity, that coupling is negligible. Okay, so let me summarize this last part. Argillaceous rock and soil subject to an increase of temperature develop significant water pressures, mainly due to this differential thermal expansion, and this may have practical consequences. The performance of that HED test in Monterrey, the one I was describing in some detail, confirms that large pore pressures do actually materialize, and they may cause damage. And the coupled formulation together with the constitutive model seem to be able to capture reasonably well the main features that are observed in the field. And then, as a consequence, we can get a better understanding by classifying, for instance, the different degrees of coupling within the different components of the problem. So I'm going to finish with some final remarks, which is a bit of a summary. These materials have a large variability of composition, grading, and geological history, but there seems to be a common core in which we can get some degree of unification across the range of materials that we have been considered. That's always very satisfying because it helps you to organize your knowledge in a more efficient way. One widespread feature is brittleness, and if you have a lot of clay fraction, you end up with a very low residual strength. And we have identified the mechanisms that are associated to the two stages of brittleness that we have observed. Also, strength anisotropy has important consequences in practice that you have to take into account. And brittleness, this is important, always leads to progressive failure, and strain localization. And we have seen examples of the two. Also, water overpressures result from the temperature increases, and they come for the interplay of the differential thermal expansivities and the stiffness of the associated material. And again, these overpressures, they reach very significant values. So if I have to summarize the talk in a final sentence, I say that the field behavior of argillaceous materials cannot be understood without considering hydromechanical coupling, and if you have a non-isothermal situation, thermo-hydromechanical coupling. Merci beaucoup pour votre attention.